Hey everyone. So this is going to be a new thing I'm doing where I try to record a recitation in place of the in-person recitations that we obviously can't do anymore. I thought it would be helpful to you guys if I posted something every Monday afternoon, since that's the day before the homeworks are due and everything, once you've had a chance to work on them, where I just kind of go through a few problems and help you out with the approaches. So hopefully you've seen the Piazza board by now. There hasn't been much activity on it yet, but our hope for the class is that students are going to be asking questions on here, whether it be homework or concepts or really anything, and helping each other out with it, really just sort of, you know, answering each other's questions and kind of uh, crowdsourcing solutions to these things. And in that sense, people will be able to help each other. Anyway, so each week I'm going to make a post, probably on Saturday or Sunday, where I just sort of request questions that people are having trouble with. I'll also take a look at what people are asking, but I just like to get a feel for what people want to see, so that I know that I'm not, wasting my time with different stuff, with things that people have no issue with. So there weren't any posts this week, but that's okay because, it's the first weekend of this and everything, and people are just sort of getting used to this. But I think you should really make it a habit to check out this form, because even if you're feeling good about the material, it can be nice to see, maybe other approaches and things like that. And maybe you'll see a question that you don't know the answer to, and that will, help you learn something. So yeah, so in the future, definitely just post here if you have any questions. There's a button to have a follow-up discussion, so you can type up, I want to see I want to see number 13 from 4.2, and then post it. If people want to see it, then they can upload it by clicking good note or helpful or whatever. Uh, and then I'll know that that's a problem that people want to see covered. So anyway, let's then start looking at 31 from 4.2. So I have a little OneNote set up with the questions that I want to look at in here. I'm not going to go through the whole thing because it's going to be a recorded video available to everyone, you know. So, but I do want to give you enough help that I feel like that you can do the problem. So I'll choose some of the trickier ones and try to work through those. Um, so for this one, for example, we are given a linear transformation, t, and it sends a polynomial of the second degree, so something that's like x squared or something. It sends a polynomial to R2, or the xy coordinate space, you can think of it as. And the transformation is defined as t of p equals the vector with p of 0 and p of 1 in it. So, and they give you a little example here where you take a polynomial and you map it through a linear transformation, and you'd plug in 0, and you'd see if you plug in 0 for t here, you end up with 3. And if you plug in 1 for t, then you'll end up with 15. So that's where that comes from. Anyway, let's look at part A, which asks us to show that t is a linear transformation. So we're looking at part A first. Right, so we are kind of given a hint here as to what linear transformations need to work. So that's pretty nice. Linear transformations need two properties. That is t of p plus q equals t of p plus q, or I'm sorry, t of p plus t of q. So that is, there's addition. There's this idea that you can add the things on the inside, and it's the same thing as adding them as two separate transforms. And then there's another one that involves a constant. We'll look at that in a minute. So, all right, what does this really mean here then, if we have t of p plus q? Well, that means we're going to want to start by looking at p plus q as sort of a function. So p plus q actually is going to be its own polynomial, and we're trying to evaluate it at 0. So this is how I'm going to write it, with a p plus q in its own parentheses there. So this is our function p plus q. And we're looking at evaluating it at 0 and at 1. So what does this really mean? Like, what if we were to graph this? What would p plus q represent? So let's look at an example. All right, so let's consider we have some polynomial p. I'm just going to draw like a kind of a parabola looking thing there, and we're going to label that p. And I'm going to also draw q, and that's going to be, I guess, a flat line up here. So that's q. All right, and then the question we're trying to ask is, what is p plus q? What would that look like? So hopefully you've some experience with, graphing and the ideas of sort of adding together two polynomials. Basically, there's a rule of polynomials that says if you're adding two of them, you can literally just add the output. So let's do that here. We have our p, we have our q. We're going to start right here, right? Because and you could label this even. You could label that this here is 0. Maybe at the peak of this thing is 1, and then on. Right. So at 0, right at 0 here, we are just left with the exact value of q because we're not adding anything from p. At 1, we are adding a little. We have this much of q, it's constant, and we also have a bunch of p. This is in fact when it's at its maximum. So our p plus q then is going to be something like this. And then if you draw it, kind of connect the dots here, we'll end up with a shape that looks like this. This is our p plus q. All right. So why am I showing you, graphing? This kind of gets the point across, I think, that adding polynomials is literally just adding. They are linear in that sense that you can literally just add p plus q, and your new function, which is just the sum of the two of them, is going to be p plus q, like a function. This is its own kind of thing. So when we look at this and we say we have p plus q of 0 and p plus q of 1, the fact that they're polynomials, and you could maybe write a little about this, is enough to show that this is p of 0 plus q of 0 and p of 1 plus q of 1. And going even beyond that, you could split this up into two separate vectors. I'm just going to draw the line here to save some time. But you could split this up into two separate vectors. And then from there, that's enough to show that t of p equals t of q. Or I'm sorry, t of, let me fix that. What I meant to write was t of p plus t of q. Sorry, I'm still getting used to the controls a little bit. So that actually is enough to show that this property holds, right? We started with this. We said that's equal to the p plus q vector here, and then we ended up eventually at here, just because of the properties of polynomials. So your next challenge, and what I'll leave you with, is showing that this is true for a constant, right? So t of cp, where c is just some constant, is equal to c of tp. Basically, you can either have the c on the inside or the outside of the transformation, and it doesn't matter. And it's going to be a pretty similar looking proof to this. So try that on your own, and if you can get both of these, which we already got one, if you can get both of them, then you've proven that we have a linear transformation. All right. Now let's see, we have part B here as well. So let's see if we want to take a look at that, maybe talk about that for a minute. Part B asks us to find a polynomial that spans the kernel of T. So I think it's worth refreshing our memory on what kernel of T is. So the kernel of T, and this is just going to be all vectors V such that, so I'm just going to write ST for such that T of V equals 0. All right, so this is all V that when you do a linear transform on that V, it gives you 0 back. And we also are asked about the range of T. I'm not going to write the range of T definition because you kind of should have a sense of that from just sort of algebra. The range of a function is just all the possible outputs of it. All right. So let's talk about the kernel one, and I'll leave you guys with the range one on your own. We're interested in finding a polynomial that spans the kernel even. So we want some polynomial that encompasses every possible kernel. So what do we know about TV being 0? Well, we know that T has this definition here, that T is, well, T of P is P of 0 and P of 1. Right. And so since we know this, and we're interested in finding the case where they're both 0, we would want a polynomial that is 0 at 0 and 0 at 1. So when would this actually happen in a polynomial? And we actually have a way to kind of to find this. I'll write this a little further over here. We know that if a polynomial is going to be 0 at 0, then it has to have a t that you can factor out of it, right? There's sort of this rule of factoring with polynomials that says if you have a 0 somewhere, then you should be able to factor that term out. So we know there's going to be a t, right? Because if t is 0, then you can plug in 0 for this t and get 0. So this is going to be one of our terms. Another term, we want it to be 0 at 1. So what kind of term can we add here that would make t equal to 0 when you plug in 1? And you might think about that. It turns out, and this is, should be familiar to you from like factoring, that if you have t minus 1, when you plug in 1 for t, this will end up being 0. So these two things will get you 0. So this is a polynomial, and then what I'm going to leave you with is, think about this. Does this polynomial here, does this span all the possible polynomials that satisfy that relationship, that t of the polynomial equals 0? Is there any polynomial that couldn't be, this or a multiple of this that would satisfy? So that then, if you can show that, you would be able to show that it spans. All right. So next up, we are going to be looking at 13 from 4.3. All right, so 13, this is not one of your assigned problems, but it is similar, and I think it gets the concepts in a way that I sort of want to show. So there's not a whole lot of work to do for this one either. We're just interested in finding the bases for the null space and the column space of A. So first, let's start with the null space. When we're dealing with the null space, we really want to be working with the row reduced echelon form. So that's our B here. Actually, B is not completely reduced. It still has a 2 as one of its pivots here. So, right, remember, if you're interested in finding the null space, we want to kind of do B augmented with 0. And I don't know if I'm going to write out this whole thing, but, we have our B here. No, we have our B, and we can imagine just augmenting it with 3 zeros. And that would provide us with a way to get to our null space. So where do we go from there? Well, where you go from there is you can get a vector x sort of based off of these values of B. And get terms for each of these constants. So x1 is going to be this first column, x2 is there, x3 is here, and x4 is the last one. So those are our 4 columns that we're getting this information from. So let's kind of do this in-between step where we gotta get it in the form of equations. Right, so we have our first equation. This is going to be x1 using our leading 1. I'm going to set it equal to, looks like we're going to have a negative 6x3 and a negative 5x4. Remember, these would actually be on the other side, and the reason I'm making them negative is because I'm sort of subtracting them over to the 0 side to get x1 by itself. All right, x2 also has a pivot, so we are also going to be able to get a formula for x2. X2 is just going to be equal to, looks like, and remember here, we're also dealing with, I do not know why my mouse thing stopped working. Give me 1 second. Okay, so here we go again. So we have our x2 here, and we have a formula for this. Now this is going to be a little bit more complicated because our x2 actually has a 2 in front of it, and maybe we'll start with the 2 there. So this is going to end up with a negative 5x3 minus 3x4. But we want x2 on its own. So in order to do that, we want to divide by 2. So that's going to give us our final equation, which is going to be negative 5 halves x3 minus 3 halves x2. So hopefully you can see the kind of the process we're going by here. We don't have a pivot in either of the last 2 columns. So we could just write x3 equals x3 and x4 equals x4. And those are just expressing that these are free variables. So we have our 2 basic variables here, which are x1 and x2. Those are basic. And we have our 2 free variables, x3 and x4. So, and that's reflected by the fact that there's no pivots in either of these last 2 columns. Right, so you can kind of see the process we go by here. We try to get it to this row reduced echelon form, which the book already does for us. And then we reduce it to these equations. Next up, we want to kind of parameterize these equations. So we have x3 as a free variable. So that means we can make a new vector. This is going to be negative 6, negative 5, reflecting the negative 6 up here and the negative 5 up here. And we also have a 1 in the x3, right? Because technically there's kind of a 1 hidden here. And then 0 for x4, because the x4 is a free variable. So this is multiplying x3. x4, on the other hand, is, well, it's going to be a very similar process, right? Oh, I am sorry. I actually missed that this is negative 5 halves. That is important. And I also noticed that I just made a mistake here. This should be a 4. Okay, so now that all that's figured out, so we have our vector for x3 here. It's a little messy, but it's negative 6, negative 5 halves, 1, 0. x4 is going to have its own vector. That's going to be negative 5, negative 3 halves, 0 because there's no x4 in the free variable, and a 1 here. And that is plus x4. So if you're trying to get the basis of the null space, all that means is we're going to take this vector and this vector, and we're going to put them in, well, we're going to bring them both into a sort of a set. So the basis, this is for the null space again. It's just going to be, I'm going to call this V1. I'm going to call this V2. You can completely ignore the x3 and the x4. We don't need those. So our basis is just going to be these 2. That is the basis of the null space of A. And the same process for any of the problems that ask for the basis of the null space. It's reduce, you get these equations, you get the vectors, and then you put it in the basis. Now we want to find the basis for the column space of A. So there's a rule for this, and it basically says that you look at the row reduced echelon form, you find the pivots. So let's find the pivots. We have a pivot in column 1 and a pivot in column 2, and nothing in any of the other columns. And then we take the columns with the pivots, we go back to the original matrix, and we take those columns. So we got our pivots from B. Now we're going to go back to A, and we are going to figure out which rows they're talking about. So here we have 1 is a pivot, so the first column. So we're going to circle the first column of A. That is going to be part of our basis. And the second column. So we're going to circle the second column of A. And that actually tells us our basis. So this is the basis for the column space of A. And it's really that simple. Obviously, if you have to reduce, it'll be a little bit more work. But really, yeah, it's just going to be -2, 2, 3. That's a -3. And our next column is 4, -6, 8. And the reason for this, the reason why this works, if you recall from really the very beginning when we were talking about what it really means to row reduce, what you're really doing is you're figuring out which columns are linear combinations of one another. So what we know from this row reduction, because there's no pivots in 3 or 4, we see that you can actually make 3 and 4 from 1 and 2. They are complete linear multiples of 1 and 2. So that means that all we actually need are the original first and second columns to create any other columns. So our basis for the column space, meaning the thing that all the columns span, is just the first 2 columns. So these are your 2 bases, and I think there's a couple of problems in the book that look very similar. All right, moving on, we have number 14. So I just want to show you how to set this one up because it's a little bit tricky. This is where we're talking about coordinate bases. So talking about writing vectors relative to a basis, other than the one we're used to, other than the standard one. But this is a little weird because it's all given to us as polynomials. So the trick here is going to be to set this up as matrices. The book talks a little bit about it. As it turns out, you can actually go really cleanly between polynomials of degree 2 and 1 by 3 vectors. So what I mean by that is we could actually set up a vector. Let's look at this basis here. So we have 3 parts: 1 minus t squared, t minus t squared, and our last part is this 2 minus 2t plus t squared. Right. So for the first one, let's basically consider it. Let's think of this top row as 1, the second row is t, this last row is t squared. And now we're going to try to fill this in. So our first column is going to be this yellow thing. Our second column is going to be the green, and our third column is going to be the purple here. It's the 3 vectors, and we're going to put them into a matrix. So here we have a 1, because there's a 1 constant. We don't have any t's, and we have negative t squared, so that'll be a -1. Second column, we have 0, 1, and -1. And the third column, all 3 are going to be filled in. We have 2. Don't know where these just went. This was a 1 and a -1. We have a 2, -2, and a 1. So that is our basis matrix. That's what it's going to look like. And we're interested in finding, we have a P of t here, so we can actually express P of t as a matrix as well. And it's just going to look like 3, 1, -6. It's really easy. You're just reading off the coefficients, essentially. And we're interested in finding what this is. So we're interested in finding P relative to B. And the way you do that, this is not too bad of a problem. The way you do that is we just want to kind of augment this matrix here, this basis matrix we just made, with P of t. So it's going to be our 3, 1, -6. And you're just going to want to row reduce this. So, row reduce it down, see what you get. Eventually, you'll end up with, your identity, your ones and zeros, augmented with something. And this something, this, whatever is where this question mark is, that is going to be your P of B. So that's what you want to find. So this problem really, once you get the setup out of the way, just boils down to row reduction. So try that out, see what you get. And you can even test it out and see if it makes sense by multiplying the constants you get here by the 3 different basis vectors. All right, so for our last problem here, we're going to look at number 10 from 4.5. So this one is looking at a subspace H of R2, and it's spanned by these 3 vectors. And the thing that we're being asked is, what is the dimension of the subspace? So we have 2 ways to do this, really, and it's kind of the different definitions of a dimension that allow us to do it. So I'm going to sort of set up this thing here that'll allow us to look at how these are similar. So these are going to be 3 kind of equivalent definitions, if you want to think of it like that. All right, so our first thing is just we're looking at the dimension of H. If I can't make this bigger. I should probably highlight it first. All right, so we're looking at the dimension of H. That is sort of our first thing we're interested in here. So what could we say the dimension of H is, equivalent to? Well, for starters, dimension of H is the number of vectors in the basis of the column space. So if we were to write the basis of the column space, that set of vectors, then that gives us the dimension. Okay, so we have that. And this, if you can, think about it, this is an equivalent idea to something we're used to seeing in matrix form when we're reducing, which is just the number of pivot columns in row reduced echelon form. So what that's saying is that if we actually took these 3 vectors here and we threw them into a matrix together, just kind of smushing them together into a 2x3 matrix, and then we reduced it, we could just count the number of pivot columns. So these are 2 different approaches, really, to doing this problem. We could either just try to look at this and figure out by inspection how many vectors would be in the basis, or we could actually reduce it and get the pivot columns. So if you were to try to do it by this method, if you were to try to count the number of vectors in the basis of the column space, we would be interested in knowing, do any of these vectors really look like any of the others? Could you make them through maybe just a constant multiple of the others or a linear combination of the others? So look at that, think about that, and see if you can figure it out. There should be a fairly obvious one here. And another thing which I think is worth pointing out is something from a little earlier in the course. If you were to put this in a matrix, right, so we have a 2, -5, -4, 10, and a -3, 6, how many pivot columns could we possibly have if we reduce this down? You can't have 3, right? Because, you can't have more than 1 pivot in a row. So if these both end up being pivots, then you'll have 2. If this bottom row ends up being 0, then you'll only have 1 pivot. But there's no way to have 3. So that gives us something right off the bat. We know that the dimension of H has to be less than or equal to 2. It cannot be 3. And actually, I should note, it could also be 0. This whole thing could end up zeroing out. Actually, I don't think it could, but there's a feasible way that you could have a 2 by 3 matrix of all zeros with a dimension of 0. Anyway, so we know there's either going to be 1 or 2 dimensions, but it's up to you to figure it out. So try to see if you can, deduce this just from inspection, or if you can't, or if you want to check yourself, actually reduce it and see how many pivots you end up with, and then it'll tell you the dimension. All right, so that's going to be it for this week. Again, next week, let me know if you have any questions, any other stuff. Um, you can always shoot me an email, ask questions on the Piazza board. So yeah, have a good rest of your week, everyone. Thanks for watching.